Hi everyone. So today we're going to be starting our first of multiple lessons on a concept called stoichiometry. So stoichiometry is very helpful for us in chemistry because it's how we can predict the quantities of either products made or reactants needed. So if you think about cooking something, baking something, you look through a recipe and you determine how much of an ingredient you're going to need to make however many products you want to form. So chemistry is not much different than that. When we are looking at chemical reactions, we want to be able to determine how much reactant we're going to use and how much product we're going to make. Think about it like this. If I'm a drug manufacturer, like making ibuprofen or something like that, I want to make sure I'm adding enough ingredients to get the desired number of products made, but I also don't want to add way too many ingredients, have excess where it's going to go to waste. So stoichiometry is the way we are able to determine how much reactant is used or product made in any chemical reaction. So it's basically our predictor. How can we figure out how much we're going to make or how much we're going to need? So to start this off, we're first going to identify what kind of reaction this is. This is actually one that we saw in the lab. So CH4 is something called methane. So methane is a hydrocarbon. When it reacts with oxygen in the atmosphere, it forms carbon dioxide and water as byproducts. So this is a reaction known as a combustion reaction. So we would see this being combustion, okay? Previous equation here where we didn't balance it, but if we did balance it, it would have a 2 here and a 2 here. So if we look at a chemical equation, let's say we're looking at this, those 2's, those coefficients. So I'm going to put a little note here. The numbers in front of a chemical. So these are the big numbers out in front in a balanced chemical equation. These represent the mole ratio of substances used. So what does that mean? If I look at a balanced chemical equation, such as the one that we see here, okay? If I look at this and I know that this technically has a 1 here, and this technically has a 1 here, I'm going to go through and highlight these numbers because these are important. Okay, we're just kind of highlighting these numbers here out in front, our coefficients. So what these numbers mean is how many moles, so the coefficients are how many moles each thing reacts with each other. So if I'm looking at, let's say, the oxygen versus the carbon dioxide, I need 2 times as many moles of oxygen as to carbon dioxide. I could write this in another way. For O2 to CO2, it's a 2-to-1 ratio. So for every 2 moles of oxygen I use up, why did I write this like this? For every 2 moles of oxygen I use up, I only make 1 mole of carbon dioxide. So we can use these numbers essentially as conversion factors. So if I know for every 2 moles of O2, I get 1 mole of CO2, I can set these up as conversion factors. So that's what we're going to do right now. I'm just going to move this out of the way here. So it asks us to calculate the moles of oxygen needed if we start with 4.33 moles of methane. So what I'm doing is converting moles of methane into moles of oxygen. In order to do this, I'm going to use the mole ratio. Okay, so let me show you how to set this up. We start with our 4.33 moles of methane, and I'm trying to go from moles of methane into moles of oxygen. So I'm just going to erase this and get this out of the way here. So if I look at my stoichiometric equation, for every 1 mole of methane, I need 2 moles of oxygen. So I set it up like this. I just use those values out in front, those coefficients, in my mole ratio. So moles of CH4 crosses out, moles of O2 is left behind, and that's what I needed to figure out. So what this means is I need 8.66 moles of O2 if I want to react 4.33 moles of methane. So I'm literally just using the coefficients in the balanced chemical equation, and then I'm just multiplying it or dividing it. So let's look at this next example. First thing, we have to balance this equation. So we have nitrogen, we have hydrogen making ammonia. So I have 2 hydrogens on the left, 3 on the right. I know I'm going to have to increase that. So let's just put a 2 out in front here, okay? That's going to balance our nitrogens, and now our hydrogens are disbalanced, but I can balance them very easily by putting a 3 there. So I'm just going to highlight these so we know that they're there. And what type of reaction this is, you have 2 reactants forming into 1 singular product. That is a synthesis reaction. So now, we're looking at our values here. So we have our coefficients out in front, and remember this is a 1. We just don't write it down. So it's asking us if we have 2.5 moles of nitrogen gas, how many moles of hydrogen are needed? So I'm going to be starting with 2.5 moles of nitrogen gas, and if I look at my balanced chemical equation, for every 3 moles, oh, I'm sorry, I read that wrong. Oopsie daisy. For every 1 mole of NH2, you require 3 moles of H2. And that's simply it. So moles of N2 crosses out. To solve this, I just multiply across. 7.5 moles of H2 are required for every 2.5 moles of nitrogen gas. So I'm using, again, these coefficients from my balanced chemical equation. They are what are being used in the conversion factor below. So let's use that same exact balanced equation, and now it's just going to be worded a little bit differently. If 0.0620 moles of nitrogen gas react, it says we have excess hydrogen. That means you can just ignore this. What that means is I have plenty of hydrogen in the atmosphere to do this reaction. I don't need to add any more to it. It just means I'm not measuring that part out. So they're being asked how many moles of ammonia, which is the nitrogen trihydride, will be formed. So I'm going from moles of nitrogen gas to moles of ammonia. So I'm going to start with what I'm given, the nitrogen gas, and I'm going to be converting the moles of nitrogen gas into moles of ammonia, NH3. This is a 2-to-1 ratio, which means we make these many moles of NH3. So literally, again, moles cross out. I'm just multiplying this across the top to get my final value. So let's look at some more practice, because practice makes permanent. So first thing, balance the reaction. So take a second, try to balance it and see what you get. So in order to balance this equation, we have 2 aluminums on the right, only 1 on the left. So I'm just going to put a 2 out in front there. That fixes my aluminums. I now have 6 oxygens and 6 hydrogens. So if I have 6 hydrogens, I'm going to put a 3 here to get those 6 hydrogens, and that also takes care of my oxygens because now I have 6 oxygens. And if we look here, we have 1 reactant breaking down into 2 separate products. This is a decomposition reaction. So looking forward, if we wanted to try to find the number of moles of ALOH required to form 2.575 moles of water, we're starting with that 2.575 moles of H2O, and I'm converting moles of H2O into moles of AlOH3. So if I look at my coefficients here, boom, 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 3 moles of water for every 2 moles of AlOH3. So moles of H2O will cross out. So now I just have to take 2.575 times 2/3. So you can either multiply everything across the top, then go back and divide, however you want to do it. But the answer you should get is 1.717 moles of AlOH3. So hopefully by now you understand how to use those mole ratios as a conversion factor. That's really all they are, and how to convert moles of one thing to moles of another.